Okay, so hi, I'm Disha. So the talk is going to be about the book. There's this book by Polya called How to Solve It. So, I mean, the talk won't be about the book, but about the contents in the book. I'll walk you through the important parts of the book. So, we're going to look at how to solve problems uh, using some of the techniques that Polya had suggested. Now, uh, just a general outline of my talk. We'll start by getting to know the book and the author. And he kind of gave a recipe on how to look at problems and how to start working on them. And then we'll you will try to do these, walk through, use this list and walk through two problems. And then I'll end with a small trivia of to do with Polya and Escher. Does anyone know Escher? Okay. Okay. So yeah, you will get to know Escher in the end. So that will be the last of the talk. So Polya, he was born in Budapest, grew up there, did his PhD and all, and then went to teach in ETH Zurich. It's in Switzerland. And I think by the time war ended, he moved to US and he was a professor in Stanford and lived till 97. Like he was 97 years old when he passed away. And he had a decently good career. And so when he came to, he's known as a mathematician and an educator, but he didn't start off as a mathematician purely. As in, when he was doing his schooling and during college and all, he used to have a lot of difficulty with maths. And when he started his work, as in his PhD, and that's when he realized that it was not him, it was the way maths was taught to him. So he kind of had this grudge towards his maths teachers and wanted teachers to teach maths in a different, better way. And so he later on gave a lot of lectures and wrote a bunch of articles aimed at teachers on how to teach, how to solve mathematical problems. And so how to solve it kind of compiles a condensed version of those notes and lectures. Now this book was first recommended to me when I was in my first year by our maths professor. And I didn't read it right away, it took a lot of time, and recently got to read a little more like carefully and looking into the detail and stuff like that. And I see that it's as good as his other books, and I'll recommend some of his books in the end. So in his specifically his maths books, I find them very kind in the way things are, like the problems are approached. As in, like, he doesn't start with, oh, you must know everything sort of approach. He's, you find that he's open to a student who makes guesses that are really bad or misses certain things which are or so-called obvious. Like a lot of things people say that, oh, this is obvious, why can't you do this or something. You can see that like he's kinder towards that sort of situations, which kind of was really nice for me because I used to have all those problems. So so mainly in the book, he says that whenever you have a problem, you first have to start with understanding what the problem is. Like so understanding is like the first step of, you given a problem statement, you understand the problem, like you find out what all you know, what you don't know, and what all can you use, and so. And then you have to like slowly plan how you're going to attack the problem. As in, have you seen a similar problem elsewhere? Like, or like, is a method that you already know something that you can use, a result that you know that is something that you can use. And once you have a decent plan in place, then you can slowly work out the problem. And once you're done working out the problem, don't drop, like that's what we generally do. We drop the problem and walk away once we're done solving a problem. Polya says that you stop and you examine your work and see whether, you know, whether it can be done in a different way. So he says this thing, like it's good to do the same problem in 5 different ways than to do like 5 different problems and walk away. Like, so you can arrive at an answer in different methods. So look at all those methods, and once you have once you've got a result, are there other venues where you can apply those results? Like in yesterday's talk, for example, you saw the oscillations being applied in various different fields. Now, of course, these are things that you intuitively do and a bit too fast, right? You never paused and thought, okay, these are the step-by-step things that I did to solve a problem. But it helps to pause and walk through each of the steps so as to like kind of make yourself comfortable with problem solving, I would say, like comfortable. Now, okay, I think I've covered most of the like. Now we'll like, I'll give you a problem. Like we'll together use these steps to like go through the problem and arrive at a solution. Okay, so we'll start with a very simple problem. So here's the problem statement. Water is flowing into a conical vessel at a constant rate. The vessel has the shape of, it should be of a right circular cone with horizontal base and the vertex pointing downwards. The radius of the base and the attitude of the cone is known. What is the rate at which the surface is rising when the depth of the water is y? Okay, so this is the problem that's given. Now, Polya says you should understand the problem so good that if I go to another slide, you should still know what the problem was. That should be the level of your understanding of what the problem is. All right. So, okay, so can someone restate the problem for me in their own words? Can someone from the, should I pick somebody? Yeah, yes, please. Mike, can you pass the mic? Can you rephrase the problem and tell me what we are looking for?
The vessel is in conical shape and it is like this.
Okay.
I mean the
yeah, like an ice cream cone maybe.
the vertex is downwards and the water is filling into it, and we have to find the height of have to find out the rate at which the height is increasing when the water is poured into it.
Water is falling into it. So that's okay. Now, so what all do we know in this problem and what do we not know? So that's the next thing that you need to pay attention to. So what do we not, like what are the things we know here? What is the given information?
The radius of the base and the altitude of the,
Yeah,
the height.
that's the height. And we also have some other information like the shape of the vessel, those kind of things. And is this all the information that you need to answer this problem? Is it complete information? Have I forgotten to give some information? I haven't given a number, like as in what is that rate. Okay, so that is okay, so that's where notations come into picture. So we don't know what that constant, like you can give it a notation, like you mark it as say R, for example. Yeah, you were saying? All that, yeah, so I haven't given that, but what the only information that I've, so that's next thing, like she says that the time in which it was filled is also necessary. Is it necessary? Is that information needed? Can we do this problem without? So that's something that we need to understand in this, like in this process of it. Okay, and another thing that he stresses on is like drawing a figure. Like whenever you have problems like this, it helps to make pictures. It helps to be able to visualize what you're trying to do. So can you guys make a picture? And also like stressing on something like this right circular cone. What is a circular cone but not right circular cone? Little off track, but can you draw what?
It's like
Yeah.
distorted party had sort of a thing.
So will the base be circular?
Yeah.
Will it be
Yeah.
of circle?
Yeah, because you mentioned a circular cone which is
No, the cross section is, the cone's cross section is circle, but will that part which is touching the base, like this one, this is like the base, will that be a circle? I take an ice cream cone, okay, and I'm chopping it in an angle and then laying it flat. It won't be, the base won't be circular. Just wanted to stress on that. Okay, so you guys have your figures ready? Okay, so this is my figure. And So what poles, so the height of, I'm calling it h, the height of the cone, and the radius b, and I want to find, so the question asks for the rate at which the height is rising, and the height of the surface is like the attitude at which the surface is at y. Yes.
Something like this,
Huh.
then how will we keep it? I mean, it's pointed, right?
Yeah, so we are not worried about like gravity and all that. Like we are in a place where, so she's asking, like, it's not a stable, yeah, use the mic. It's not a stable, you can't, it's not a
Just
stable equilibrium
pointed.
to keep
I mean,
it like that.
it won't keep.
Topple. Huh. So yeah, that's another thing. Like I have a stand.
Sorry?
Or I have a stand, I'm holding it, any one of
makes
that.
sense.
Yeah.
Since it's not mentioned, I was confused.
So like isolated situation, okay? It's, that part is taken care of. Yeah? Anything else? So, and the rate at which this, the height is, the water is being filled in, I'm denoting it by R. It's to make my solving easier. What I will have to find out is the rate at which this height is changing, right? So t is denoting, t denotes time, dy by dt is essentially what I'm trying to do. Okay, so what are the, so how can you relate all these unknowns with all the things that you know in this? Can you guys think of relationships between all these notations that we have, h, b, x, y, r, dy by dt? Forget about dy by dt, r and all those things. Yeah.
H is the maximum point.
Yeah, h is the maximum height to which it can fill. After that, it will like go out. Yeah. Like h is the height, okay, and b is the radius. Yes. Now, how are these things related? Like, how is h and b related to x and y? Yeah. So that gives you that not only gives you a relationship between all four of them, but mainly it gives you x in terms of y, right? Okay. Now, what does r have to do with the rate at which the water is filled? What does it have to do with the volume in which the amount of water that is there? Why are we worried about density? No, so the R is the rate in which I'm pouring in water. It is, let's say it's in the dimension of that is meter cube, if I'm using SI units per second. That's the dimension. Okay, so volume per second. Yeah. That's the, or liter per second.
Yeah, would the answer change if we replace water by mercury? That's a good question to ask.
Huh.
Yeah. So someone there was talking about the density. Is the density necessary? Like suppose they make mercury instead of water. The flow rate is given in volume.
Volume, yeah, volume per second. Volume per time.
Yeah. So
then I shouldn't worry about
the density.
Then I shouldn't worry about the density. So she was saying that we need to worry about the density of the fluid. And her reason was, yeah. Yeah. Okay, so that is an information that I had left out when I gave the problem. So here is it. It's in the dimensions are volume per second, like volume per time. Okay. And okay, now that we have certain things in picture, like one person gave me the relationship between x, y, h and b, right? Since it's a right circular cone, it will follow those rules, right? Okay, can you put it on the board? Can take the chalk. Okay, another person. The relationship between the volume and the rate. Yeah, can you put it on the board? H by y is b by x. Okay, is that correct? Yeah? Yeah. So how is the rate at which the volume is filled to do with, let's assume that it's filled up to the height x, okay? And so, do you know the volume of a cone? Yeah. Okay. So how is
The volume at some time is equals to T, 1 more cone of 1 by 3 pi r square h.
that's the volume of the cube, yeah. Yeah. H is?
And if the range is r and the time is t, then it's
Yeah, or I can also be like rate is rate in which it's filled is also the rate in which this thing changes. This is actually just the volume. This is just the volume of that part. Yeah.
if I differentiate it, I could get
Yeah. Okay. So if you differentiate it, like, but why would you differentiate the volume? Yeah. So, but why? But that is R. Yeah. So that is how the R is related to the volume, right? So dV by dt is R. You can forget about the rest. Think about V and R and how are they related. Anybody else? Yeah. Yeah. That's it. Okay. So that's how volume changes with reference to time. Can you give her the mic? Okay. Can you explain what you're doing?
Hello. So R is dv by dt and x by y is equal to b by h from that relation. So now we want to find dy by dt. So we have to eliminate x square. So we can substitute, since this is constant, we can substitute value of x from here to there. So we'll get v equal to 1 by 3 pi b by h y whole square into y. Now dv by dt will be equal to 3 and y square pi b square h, right? H square, yeah. Now
Times?
times dy by dt. Now they asked us to find the rate at which the height is changing at h. So this will replace with h, and then we'll get
No. At any
okay.
y. See,
Or
wait a second.
at any
At
point,
any
then
y.
it's done. Yeah,
Yeah.
then it's fine. Then this is r, and then you'll get dy by dt equal to r h square divided by y square pi b square.
Yeah. Is everyone else convinced with this? So this is what we did. We can. Okay. So this is the solution. Now, so we are done now. And generally what we do is like we wrap up now that we have the solution. What I'd like you to do is like think of where else we can apply this. A. B. What are the what are the other places where, like one is what are the other places where we can apply this. Next is can we use this to solve other problems? Can you think of other problems in which we can solve this? And can you think of different ways in which we can solve this? Like different way to solve the same problem. Can somebody think of one? Yes?
okay. How I solved the problem was, instead of writing v, I wrote dv first.
What? Okay, dv, okay.
dv as like
Small
pi
change in volume.
Pi x cube x square dy.
Okay.
And then and then divide by dt and substitute for x.
Okay. Yeah.
That was shorter.
Okay. 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 And where else can we, like, how do we, once we are done with the problem, like, how do we check whether our solution is correct? Like, can you think of, yeah, dimensional analysis is one way to do it. So, are we dimensionally sound? Are we dimensionally sound? Do we get, so we are supposed to get distance by time, right? On the left hand side, we have distance by time. What do we get on the right hand side? Do we have distance by time? Yes?
Because R is volume, like so meter cube, and then h square, so that's
Yeah.
And in the denominator, we have y square d square, so both of them are lengths of
Yeah.
4, so it gets cancelled.
So dimensionally we are sound. Okay. Now the next thing I want you to do is work out a different problem. But in this case, instead of a conical vessel, I have the frustum of the cone. So this is what I have. Let's say the smaller radius is A and the larger radius is B, and water is being filled in, okay, at the rate R, and the height of the total height is h. Can you solve this problem using the same technique? Like A. This is A and B. Can someone work it out? Yeah. Do you want to come on the board? Like, I want, give me the
If you write
equation
dv
for,
first, whether the cone is complete or if it's a frustum, that doesn't matter. You can just write dv.
yeah. So can you put dy by dt for this situation? Can you put it on the board?
But we'll have to find.
At the height.
Okay,
at
we'll
the
have to
height
find
y,
the complete height first.
The complete height is h. I want the
No,
rate.
like complete height if the frustum is extended to be a cone.
Others, please work out meanwhile in your own way. Hey, write it bigger, no? A little bit bigger. So I want dy by dt in this situation, which is like I'm asking for the rate at which y is increasing as I'm pouring in water at constant R. Okay, can you work it out in the notebook? Work it out in the notebook, or like
H by b minus a, and then h is
somebody help her?
into 1 plus a by b minus a. And now in the same
Okay,
thing.
wait. Before you go ahead,
In
explain
the
the
same-
steps. Wait. Explain.
Instead of xy by equals b by s, you write xy by y equals
Yashaswini,
b by
explain the
h.
steps.
Okay.
Explain the steps.
This is just some algebra to find out the total height. If the frustum is like extended to be a cone.
And then?
Algebra.
Yeah, explain the algebra. Walk through the steps.
Okay. The ratio of a by d, if the extra height to be added to get the height of the full cone is d, then a by d will be equal to b by h by d.
Yeah.
And then find d.
Okay. And then
And
the
total height is h plus d.
Yes.
And now here instead of b by small s, you write b by capital S, that is b by h into 1 plus a by b minus a.
Convinced? Yeah. Then?
And then dv is pi x square y, right?
Yeah.
And x is that. Rearranging.
Yeah, substitute it. You guys can help her. That's not dV. Now you're doing V.
dy.
No,
Yeah, dy.
You are doing Y.
And then
No. You're.
we need
Can you guys?
we need it in terms of.
Wrote down the volume first.
We need R in like this is R. Just put everything. That's it.
That's dimensionally incorrect. Can you check it? Can you write
See,
down first?
dimension. This entire thing has no dimension. Pi y cube has the wall. Okay.
You notice that there is an extra
Oh, yeah.
length dimension. Yeah.
Wait.
Yeah. Can you do the rest?
X square dy.
Come. I'll help you.
Y square there.
Come, I'll help you.
Like because there's no Y, right?
Can you come? I'll help you. Come. It is right. Come. So write down the volumes formula first.
This is right?
Pi by 3. It's not dV. That's V. Can you do it? She'll show.
This is dV.
X depends on Y.
Yeah.
You have to. Yeah. You haven't. So there. Whenever V changes, X changes. Sorry, X change. Whenever X changes, V also changes.
Yeah.
So.
V and then you substitute X and then you take dV by dt.
Yeah.
Yeah, I did substitute. This is me substituting for X.
In that case, like this power will change, right?
Oh,
Like if you
this is y square. Yeah, that's all.
and then
Yeah.
3 will come down.
That was just copying mistake.
No, but like won't it still change?
Yeah. Write it down.
This is the right answer, I'm sure.
Okay. Yeah. Please do it.
If the answer matches, then we can be sure that I'm right.
Yeah. Yes. No. Can you get V first? Yeah.
This is V, right?
Pi by 3. Yeah. And then you substitute X.
And X is?
X is, yeah, X,
This one.
yeah, here. B by H. B by H. Yeah. And square the whole thing. B square also gets squared. H square is squared. Yeah. Now you do dV. That's how you lose the pi by 3. The by 3 in the pi. Okay, so that
And
would
also
be,
one thing, this and this are basically the same, but instead of h, now the new h is h into 1 plus a by b minus a.
yeah.
So if you know this answer, we don't have to find this again, just replace h with h into 1 plus a by b.
Yes. Okay, so now can we go back and verify whatever we have derived there using the frustum of the cone? That's what she said. Can we do that? What's the difference between the frustum of the cone and the cone?
Like the frustum is a part of the cone.
Yeah. So if I make A go to 0, then I have the cone, right? Yeah. And then does our equations match? Does our result match when A goes to 0? Just check that. Yeah, when A is 0 in the new, does it match? So that's one way we can check. Another is, now instead of a cone, what if I had a cylinder? What can we say about the rate in which, now right now the rate is depending on the height, right? So the height at which it is increasing is different when the height is, like, it's dependent on height, right? So what if it was a cylinder, like a uniform cylinder? Then would it? But the question is like, will it depend on the height? Should the rate at which it, like, as in it, is it height dependent, or will it be a constant like the rate in which you're pouring the water in is? Okay, okay, one way to check it is when you have A and B the same. Okay, there it goes to, yeah. When you have A and B same, yeah, so you'll mostly have 0 there, 1 plus 0.
No, if we shift that up, because there's a denominator in the denominator, right?
Yeah,
so
yeah,
that
yeah,
would
yeah.
go up eventually.
Yes.
So it wouldn't be.
So can you check that?
Okay.
Can you substitute B
Like
is equal
B
to
is
A?
equal- yeah,
Yeah,
yeah.
substitute. It will be in the numerator. It's in the denominator of the denominator. Yeah. So the rate, of course the volume is increasing, but the rate at which it is increasing, will it be height dependent? As in, let's say I am pouring in water 2 liter per second. Okay, that's too much, but let's assume. So the rate at which it is, what did you get as 0? dV by dt or dy by dt?
dy by dt. Because that's the formula for
So
dy
the
by
rate
dt.
at which the height is changing is
Yeah.
constant.
Yeah.
Okay. Yeah. It should, like,
No, that y square doesn't matter over there, na? Because if we say b is equal to a, b minus a from
you should get a constant. You should get a constant that's independent of y. If I'm pouring in water in a cylindrical vessel at a constant rate, the height will also increase at a constant rate. So that is something you can verify by putting b is equal to a in the frustum of the cone. Okay? Can you do check this? Fine. And the question is, go from the cone to and verify whether your cone result is correct by using the results of frustum of the cone. Okay? For the frustum of the cone, if you take the base radius as 0, you are in a cone. And if both the radius are the same, then you are in a cylinder, right? And you know for sure that, I mean, you know from observation at least, that in a cylinder, when you pour water at constant rate, then the height increases at constant rate. So the solution you get when you do A equal to B should be a constant, independent of the height. It shouldn't change according to height. So this is a way to, there is. Do work this out, like.
Maybe we should ask them what happens when you put B equal to A in that.
Yeah, so they're saying 0, but it shouldn't be 0. Shift it to numerator, it's in the denominator of the denominator. Yeah. Oh yes, correct, yeah. Yeah. So shouldn't it be like 1 over 0 sort of, sorry, that sort of situation it will be, right? Yeah. So, okay, so we have, can you, okay. Okay, so this is the constant, like here, this is R. Okay, so we have, so dy by dt is, dy by dt is some constant times h square over b square y square. It should get cancelled with the other way. So, one plus a over is that squares then when we have A is equal to B, you should have a constant. Verify this thing, please. Yeah, we are missing something either from that or. Yeah. Can you guys check this? Shall I go to the next one?
P goes to A, the denominator has some infinity.
Yeah.
So the whole thing will go to 0, but the rate is finite.
The rate is fine. It should be finite.
Finite, yes.
Yeah, that is how it should be. So, like something wrong with our.
Something wrong with the.
Yeah. Yeah.
My notation is all different.
Huh.
But for a frustum, it would just be this. I mean, this is y, I suppose.
Yeah.
Right circular. So this constant is still there. And when
Yes.
you have the r square, it will have this constant part, which when it goes down, this tan alpha is 0. And
Okay. So it's the initial. Okay. Okay. Here's what. Rederive this part. The rate at which, rederive the volume formula and the rate at which it is changing. When for a frustum, you will still have A and the ratios in the picture and the difference. Just rederive that. Okay? Yeah. There is a chance it probably is not. It's. Yeah, that's why the frustum of the cone equation solution is not right. Yeah. So when we took the volume, we took this entire volume, which was not necessary. We just need this. So yeah, that was the mistake. So when we did this, we took the entire volume, not just the frustum. So you need to subtract from the volume formula, you need to subtract the bottom cone, which is this height, pi by 3 a square, and the small height, which is, that was derived here. D. Oh yeah, what was D? D came out to be? Huh. Yeah. Can you tell that? Okay, so you will have this, and that should help take care of. So no, I want this volume, just this volume. I don't want.
Yeah, the y is the height of the cone, right? So we haven't accounted for that.
So here, oh yeah, you're right. So this is where we need to. That height is also different, yeah. Okay, redo this part, please. I'll go to the next one. When you redo that part, take care that the volume, that initial volume that you consider is not of the whole cone, just the frustum of the cone. So the height y, when you calculate, keep that in mind. That's another mistake that we made. Okay? Yeah, so I think this is also like a, maybe don't skip steps, like pause and look at stuff. And yeah, so this is also a lesson in like how to check your answer. Like if our formula was correct, it should have worked out for the the cylinder, right? This is a way in which you can verify. Okay? And okay, I'll go to the next one, running short of time. Yeah. So you guys, I want you to like do that as an exercise. So this is, Polya also emphasizes on the use of analogy, as in the way you can like solve a problem using problems that are already solved. Like you kept seeing that throughout this week, right? So for example, in Rajaram's talk, you had this Sierpinski gasket, and the problem was to find out the dimension of the Sierpinski gasket, right? Sierpinski carpet, it's also called. Where else have you seen such kind of pattern appear? You guys are familiar with the binomial theorem and the Pascal's triangle. Have you looked at the Pascal's triangle when you do mod 2? Like take the Pascal's triangle and divide all the numbers by, do mod 2 on each of them. So you'll have like a triangle full of 1, 0, 1, 0. Okay? Make it later and look at it and see how Sierpinski gasket looks. Not right now. Okay. So this is like a really old problem. Like it's called the Basel problem because back in that time, when like Newton, Leibniz's time, when calculus was still new, people were trying to solve this, and Bernoulli also was one of the people who tried solving it. And Euler is Jacob Bernoulli's student, and he kept coming up with approximate solutions, which Bernoulli wasn't happy with, and who wanted like exact solution, and so did Euler. Euler also wanted exact solution. So today we'll try to like solve this problem using Euler's approach, which uses this concept of like analogy a lot, like using already solved problem to solve a new problem in hand. Okay. Now you guys, so let's do the first step. First step is like understanding the problem. So what do I have here? It's an infinite series, and I'm trying to find out 1 plus 1 by 2 square, 1 by 3 square, sum of all that. So like I'm summing the reciprocal of squares, right? So if I expand it, looks somewhat like this. If I add the first 2, 3, I'll get like 1.25 if I do the first 2. So it's surely more than 1, yeah. Is it more than 2? Okay. Why are you so, how are you so confident that it is not more than 2? Maybe like I'll argue that, I'll take all the small ones, add up, and maybe it will be another 1. Is that possible? Anyway, so Euler, who was working on this, he did find the solution. He came up with many approximate ways to get the solution, and his solutions were good up to like the 7th decimal point. It's around 1.66 something, and he was good to the what is it called? The 7th decimal point. And so so the approach that Bernoulli used was that, calculus is new. We are not using calculus to solve this problem. What was known very good back then, or around the time when these things were being discussed in Basel by these people, was that any function you can like use Taylor expansion. Okay, and once you have Taylor expansion or like power series, you can treat it like a polynomial, and all the results that are known for polynomials can be applied for the power series. So that's when like something like very algebraic is being used for how to put the other one. Okay, the point is that the tools that were developed for one school of mathematics or one topic is being used to solve problems for another one. So okay, can you guys tell me what is the problem we are trying to solve? Sum of reciprocal of squares. Okay, so we'll also like walk through what Euler did and try to find out the sum of reciprocal of squares. Okay, infinite sum. Now the third statement, I'm hoping that you guys already know this, but if you don't, we'll like work it out. What it generally says is that if you have a polynomial, n degree polynomial, so it's something of the form a0 plus a1x plus a2x square plus so on up to infinity, sorry, up to n, you have a polynomial, then it will have like n different, hoping that it has n different roots and the roots are known. Okay, then you can always represent it in the form of and so on, right? If I know the roots of the polynomial, yeah? Okay, and if this is the polynomial, let's say, okay, I think I have to rewrite it as just to match the yeah, alpha n. So these two polynomials, so this is a naught and this is alpha. Alphas are the roots, okay, a naught are the coefficients. I can match the coefficients, right? So that's exactly what Euler used to find out the sum of reciprocal of squares, okay? And the function that he used was, so this is something I'd like someone to come on the board and work out. Who wants to come?
You call out a group name.
Yeah.
And let them choose somebody from it.
Okay, so group 12. Group 12? Where is group 12? Ah, okay. Oh, you guys have been coming to the board a lot. Maybe I like you should the group right behind. What's your name? Yeah, no, person behind you. Harini, yeah, can you come? Yeah, so this, I'll explain to you if you don't understand. So if you're not understanding, please ask right away. It's okay if you ask in between, it's fine. Okay, so what we are trying to do here is that we are trying to okay, let's say, and the roots are, yeah, these are the roots. Can I, so I have written the polynomial as is this good? Like as in the power x to the power 0, what is the coefficient of x to the power 0 in this equation? A naught. And then in this equation, what's x to the power 0's coefficient? A naught. What's x to the power n's coefficient in this equation? Yeah, and what's x to the power n coefficient in this equation? an, sorry, yeah. Somebody else? X to the power n's coefficient. All the way to alpha n. What about the signs? Yeah. So an will be equal to, so I am comparing the coefficients. An will be equal to a naught times minus 1 to the power n times 1 over alpha 1, alpha 2, this is, yeah, is this fine? So, okay, yeah, can somebody explain? Yeah, yeah. So on the first line, I have a polynomial. Like, okay, let's consider like a quadratic equation. I have something of the form, gonna pick something easy. 6 minus 5x plus x square. Okay. So here a naught is 6, a1 is minus 5, an is 1, right? So this is a quadratic equation. I can write it as 1 minus x over 2 times 1 minus x over 3 times 6, right? Yeah, convinced? Can I do this? So why was I able to do this? Because I know that 2 and 3 are the roots and 6 is just a naught, right? So I can do this for a polynomial of degree n. Yeah. And once I know this, the first question I had asked was what's the coefficient of x power n, in this case x square, in the first equation and the second equation. So how do you get x square? You get x square when you multiply these two things, right? So it is 6 times 1 by 2 times 1 by 3, which is 1, and that's the same as the coefficient of x square here, right? How do you get the coefficient of x, which is x to the power n minus 1? How do you get that? So you multiply with everything except one of it, and then add with whatever is remaining, right? So yeah, you guys are lost? Say something, please. Yeah, it's fine. Okay, so the point here is that you can compare the coefficients of both the forms. If you have one form, you can get the other form, right? Now, Euler approaches the problem using sin x. Who remembers the Taylor expansion of sin x? Is it 1 minus or x minus? X minus, okay. So can you write? They'll tell you. So sin x is equal to, so this is like the power series expansion of sin x, right? Sin x is equal to x minus. X cube by 3 factorial, okay. Yeah. Now, okay. So I can't apply this rule of this thing if my like if this equation is 0 at 0, like if my f of x is 0 at 0. So I'm going to get rid of that by dividing both the sides by x. Okay. If you divide both the sides by x, what do you get? Okay. So, okay, now sin x by x, what happens when x goes to 0 or limit of x goes to 0? It's 1, right? What are the other roots of sin x by x then? So in case of sin x, the roots were 0 and what are the roots of sin x is equal to 0? Pi, 2 pi, 3 pi, 4 pi and so on, right? Now in the second equation, what are the roots? No, roots, as in for what values of x will you get sin x by x is equal to 0? N pi, any n pi, right? Okay, so you have an equation here, right? This is this equation, right? And you have the solutions. So the solutions are, the alphas are, where are the alphas? Okay, so the alphas are all n pi's, okay? So which means that I can write the first equation in this format. Where is that? Yeah, in this format, using the alphas. Can you do that? So, okay, another thing, note that these are like squares. Okay, so instead of x, you will have x squares. Okay, that's another line that I've jumped. If anyone is not clear about that, we can discuss it. Yeah, do that. So you can rewrite, so this is the equation that you have written, right? I want you to write it in this format. Using these alphas would be pi's, like pi, 2 pi, 3 pi and so on. Technically squares of them actually. So pi square. So the way it comes is you have 1 minus x over pi, 1 plus x over pi, because you have plus pi and minus pi as the answer, right? So together I'll have 1 minus x square over pi square, right? So x square over pi square. Next one, louder. Two pi square, x to the power 4, 2 pi ka square, the whole square, 2 pi, yeah. And then all up to infinity in this case, right? Can you write one more maybe? Now let's compare the roots. Okay, what's the coefficient of x square in the first equation in sin x by x? What's the coefficient of x square? No, x square. 1 upon minus 1 upon 6. Yeah. And what's the coefficient of x square in this equation? Is it what? No, not. Okay, this whole thing is a product. I'm not asking the coefficient here. The product, in this product, what's the coefficient? So I need to take x square from each of them and multiply with ones, right? That's how I get x square. Like I take this, multiply with 1, 1, 1 and so on. So I'll have minus x square over pi square, right? Times, then again I'll pick this one and multiply with the ones, right? Plus x square over, minus x square over 2 pi square and so on. That is the coefficient, like that would be the x square's coefficients, right? Is this clear? Coefficient of x square. So what would that be? Can you write it? It will be like minus 1 over pi square plus 1 over, 3 pi whole square, 4 pi whole square and so on up to infinity, right? Now you get rid of the minuses on both sides and send the pi squares to the left side. So what's pi square by 6? Yeah. So that gives you the reciprocal of, yeah, good. Okay, can you guys use the same technique to do sum of, yes. So 6 is the coefficient in this expansion, 3 factorial, 1 by 3 factorial. So n factorial is n times n minus 1 all the way up to 1. Okay, so 3 factorial is 3 times 2 times 1, 6. So in the sin x, I'm taking the common terms. I'm comparing the coefficients of x square. Yeah. So when I did, okay, not here. So when I did sin x by x, I have x square over 3 factorial here because I divided by x. And that 1 by 3 factorial is what I got as 6. Yeah? Anybody else? So why do? Oh, because so okay, that's another thing. Like another part is like this, that you recognize the patterns here. As in, he was also like trialing with a lot of other functions at the same time, and he ended up finding solutions for other some series, which is also something you guys will be working out soon. Like what happens if you do cos x? Cos x is equal to 0, or like tan x is equal to 0, or logarithm of x, these kind of things. There are, it's also like a way to, like he found solutions to problems he wasn't even looking to solve after solving this. Okay, when Euler was dealing with polynomials, his original intention was not to solve 1 over n square. As in, he didn't, that's the whole point of analogy. Like the fact that the problems that you solved in one arena might end up being solutions to problems that you have in other arena. So it so happened that Euler was dealing with both of these things, had access to both of these things. And so he did cos x, and he did, so I want you guys to try and get to, wait. So that's the exercise. I want you guys to try and get to reciprocal of 4 powers. That's the exercise for you guys. Okay, and like 1 plus 1 over 2 power 4 plus 1 over 2 power. Can you manipulate this equation here? So you will have 4 powers instead. So 1 plus 1 over 2 power 4 plus 1 over 3 power 4. That's what I want you to find out using the same technique. Like you pick a function, expand the function using power series, apply all the rules that you know for polynomials. No, I won't tell which function. That is what I want you to figure out. So this is like you are studying the power series, but you are solving the solutions for infinite sum. Though that's not, yeah, that is what is happening here. Okay, and like this is one example of analogy, like how you have solutions in one place, but you apply it in other arena. Okay, like that Pascal's triangles, Sierpinski gasket. That's another exercise that you guys should try out. I don't know whether you have already solved the dimension of the Sierpinski gasket. Did you guys get the solution yet? No? Okay, we'll work that out too. Okay, next thing is I want you to, okay, this is also a takeaway. Yeah, so this is the function. Yeah, this is a function 1 minus sine x. Actually, do we have time to work this out now? Do we?
Maybe you can give it as
I want to
homework.
get,
Both these problems
yeah,
as
as Madhava series. Okay, so this is like a very popular series called Leibniz formula for pi, but then we also know that Madhava also came up with it independently by himself. Yeah? Yeah, after we factorize. So after we factorized, we compare the coefficients of coefficients of same power terms. Like in this case, in this small case, we are comparing the coefficients of x square in this equation and this equation, right? Similarly, we are comparing the coefficients of x square in this equation and this equation. In this equation, the coefficient is 1 over 3 factorial. That's clear, right? What is the coefficient of x square in this equation? If these two equations, like if these two terms are same, I mean if they mean both of them are like the same function, then they should have same coefficients as well, right? As in this is the power series expansion and this is the polynomial you write because you know the roots of this equation. Yeah? Yeah. So you compared those two and that's how you arrived at 1 over 3 factorial is this summation. Yeah? Is it convincing? Okay. So we move to 1 minus sine x. Again, I want you guys to like do the same thing. That is your function. And the objective is to find out the power series expansion of pi. Sorry, not power series expansion, like the series expansion of pi. It's an infinite series. And that's also like the popularly known as Leibniz formula for pi, but Madhava also came up with it around or before Leibniz did and published it. Okay, so I think I'll wrap up. Is it? Oh yeah, about the yeah. So I want you to. So this is now instead of sin x by x, I have a new formula for you, which is 1 minus sin x. So in place of sin x, you can substitute the series expansion, and you know the solutions for 1 minus sin x. What's the solution for 1 minus sin x? Is equal to 0? So pi by 2, odd multiples of pi by 2, right? So pi by 2, 3 pi by 2, 4 pi by 2, plus or minus. So you can write it as a polynomial and then compare the coefficient and get a series expansion for pi. It will be like 4 times, okay, I won't give the answer. You guys should work that out. Yeah? And so I'll stop. So Polya, the person, this is the next part. The Polya, the person was, he came very late into mathematics and therefore it had its own merits in the sense that he got to like explore like maths in a very leisurely way is what I would say. As in, okay, leisurely in today's terms, as in he wasn't concentrating on one small topic. He actually has worked in a lot of topics within number theory. So one of it is symmetry groups. What I mean when I say crystallographic symmetry groups, and so what it means by 17 plain crystallographic groups is that, let's say I am tiling the floor or the wall or something like that, and I'm repeatedly using the same pattern. Okay, so give me any pattern, it's going to be one of the 17. Okay, so there are like 17 symmetry groups when you do 2D tiling using repetitive patterns. Actually, when you, instead of a plane, if you tile along a line, you have 7 groups. This is called freeze groups. I have not put it in the slide, but just trivia. So if you take like take a sari, the border of the sari will pick any border, it will belong to one of those 7 groups. It's called the free, okay, the hand weaving, silk sari weaving machines in different parts. So these patterns are formed by translation, reflection and rotation, right? So these different parts have machines built in such a way that you can notice that Kanchipuram saris follow a different group than the Banarasi saris, or like that, like because of the machines being manufactured in that way, you can pick a sari and look at the border and tell which kind of machine they used. But because the machine will have fixed like possible kind of designs. So it might be able to do only rotation and this thing. Like when I say border, I mean like you will have that mango flower, something like that, reflection. You must have seen a common sari border, right? Like that. Similarly, now instead of a linear line, if you have a plane which you are tiling, these are like 17 groups. And Federo or somebody, I can't remember the name, that is the person who came up with the proof that this can be done only in 17 unique ways, only in 17 ways. And Polya also independently showed that it can be done in 17 ways, and his paper was illustrated. As in like, this is a page from his paper that said this. And he was in touch with this artist called Escher. And as in they were in correspondence. And this actually inspired Escher's work, a series of woodcut blocks called Metamorphosis. So this work is inspired by a mathematician's journal paper. So this is Metamorphosis 1 and this is Metamorphosis 2. The artist is MC Escher, is very popular for making these symmetric tiling patterns. And these are actually woodcut, as in carved in wood, and they later used for printing. I don't know where the originals are, but yeah, that's Escher's work, Metamorphosis 1 and 2. And they are known to be inspired by Polya's paper on the crystallographic groups, these 17 crystallographic groups. Now, if you guys want to make, you guys want to play around, generate patterns using those 17 groups, you should check out this webpage called Escher Sketch, where you can like put in the pattern and play around. And this book that I have recommendation for is Polya's other book called, he has written multiple books, I think around 11 to 17 books. And I would recommend this Mathematics and Plausible Reasoning. It's a bit more expansive than How to Solve It. Very kind and nice, like goes through a lot of mathematics problems in really fun ways. Yeah. So with that, I stop and we wrap up. Yeah. Any questions? Yes, questions. Yeah. Okay, yeah. So okay, let me do it properly here, or maybe. Okay, so here is what is happening. The first line you see, that's the expansion for sin x. That part is convincing. Yeah. Power series expansion of sin x. That's x minus x cube over. That part is fine, right? First line is good. Now So we divide both the sides of the equation by x to get rid of that root which is 0. Okay, because that polynomial rule that we have doesn't work when f of x goes to 0 when x goes to 0, like when, yeah, as in you want the constant coefficient to be non-zero. Yeah? Yes. No, we are not manipulating the question. We're not manipulating the question at all. So what has happened here is Euler noticed that this is a pattern that appears when you consider two ways in which you look at functions. Like one way to look at a function is to treat it as a like a power series expansion. That is one way to look at it. So here's what is happening, like you have the power series expansion, which is like you have a function that you can do power series expansion of, and then treat that power series expansion as a polynomial. So this is what is happening. So these are sort of like independent things. Treating a polynomial using all the rules, like exploiting all the rules of polynomial is one thing, whereas power series expansion of function is one thing. Okay, so yeah, so this is what we have, right? So this is the equation I have, 1 minus, I'm just gonna do this for now. X minus c and so on. So for this equation, you guys agree that ABCD is the solution? Yeah? ABCD is the solution of this, and essentially I'm trying to ask you to find the coefficient of x, right? Okay, I can just put x square if that's fine. That's what is happening there, right? So what I've done is I've taken minus x square a, okay, and multiplied with 1 from all of them, right, plus minus x square b and multiplied with all the 1s. So when I'm expanding the product, the way I can get, okay, how will I get x power 4? I pick 2 of the x squares and the rest of them I'll multiply with 1, right? Yes? So if I do that, the way I can get x square's coefficient is I do minus x square by a minus x square by b is multiplied with all the 1s, minus x square by c minus x square by d and so on, right? So I'll have minus x square times 1 over a plus 1 over b, so on. Is it making sense? I don't think so. Yeah? Okay, let's ask a different question. Find the, let's work with like a finite polynomial, okay? My polynomial is 1 minus x over 3, 1 minus x over 5, 1 minus x over 4, okay? If I am expanding this and writing it as a polynomial, then what would be, like I'll take 1 times 1 times 1, like I'm expanding this brackets, okay, plus x times, I'll have, so this is minus 1 by 3 times 1, okay, minus 1 by 3, sorry 1 by 5 times 1, minus 1 by 4 times 1, right? That's x's coefficient. Technically it's the, like I'm just summing all the reciprocals. For now, what about x square? X square would be minus 1 by 3 times minus 1 by 5 times 1, right, plus 1 times minus 1 by 5 minus 1 by 4 plus minus 1 by 3 times minus 1 by 4. Yeah, that would be x square's coefficients, and x cubes would be minus 1 by 3 times minus 1 by 5 times minus 1 by 4. Like when I'm expanding, I'm multiplying with a term from each bracket, right? So how should I multiply in such a way that I'm getting x only? That's like you pick one x and the rest of them are constants. You pick the constants. Yeah, that makes sense now? So that's how, so in that equation, instead of x, I had x square. So what I did was, all the terms had x square. Like it was 1 minus x square, 1 minus, like 1 minus x square over something, 1 minus x square over something. So I was picking 1 x square and multiplying it with the constants from all the other brackets. Yes? And then comparing it with the other equation. Make sense? Yeah. Any other questions? No questions? Okay, so I have, if you guys are interested in tiling, I have some tiles in my office. When later, when things are like a bit more smoother, we can play with them. Yeah. So if everything is up, we can wrap up, go for a break and come back for the next talk. Yeah.